Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book, 3 volume series I wrote from 2019 to 2022. Each of these volumes is available on Amazon.com in case you're interested. You can either search for the Math Lovers book or for my name, David Tear. They're $30 each, paperback, or $9 Kindle. I think they're a good buy. You might want to check them out. Anyway, and I'm doing a free feature on the Math Lovers book on this channel. I'm going through the first 2 volumes, which are sort of the text volumes. Volume 1 is more recreational math, and Volume 2 is more sort of academic, a little bit more advanced. But anyway, I'm up to section 3.4, and that one is on Fibonacci numbers and the golden ratio. And this is the last section of chapter 3 on irrational numbers. So anyway, let's just begin. So anyway, I have videos on this channel on Fibonacci numbers. As a matter of fact, I think some of the first videos I made on Dave's Math channel were on Fibonacci numbers. So if you want to learn about them in more detail, you might want to watch some of those. But I also talk about them in my book, and I think most of you guys are probably familiar with Fibonacci numbers. They're pretty well known sequence of numbers, and they have a pretty simple definition. Usually, the way you're defined is you say F0 or F1 and F2 are both equal to 1. First 2 elements of the sequence are equal to 1, and then you get each new element of the sequence by adding the previous two. For instance, F2 would be 1 plus 1 or 2. F3 would be 1 plus 2 or 3. F4 would be, or F5 is 2 plus 3 or 5, and so on. Keep going like that. And they grow pretty quickly, as you can see. F20 is already 6,765. But they were introduced by pretty famous medieval Italian mathematician named Fibonacci. Actually had a lot of different names. He was a monk. I mean, there wasn't a lot of math in Europe in the Middle Ages. It was the Dark Ages, and there wasn't a lot of intellectual activities. You guys probably know during the Dark Ages. But there was a medieval monk who was also, I guess, a recreational mathematician named Fibonacci. And I think one thing most people don't realize about Fibonacci was that, everybody knows him for the Fibonacci sequence. But I think an even better, a more significant development that he made was that he wrote a textbook on math. I think it was about 200 pages called Liber Abaci. And he basically introduced our modern system of doing arithmetic. He introduced the decimal system because I don't think Europeans were using decimal numbers until Fibonacci introduced them in around 1200 AD, before they were using Roman numerals primarily. And not only that, but he gave all the rules that you probably most kids learn in elementary school for doing basic arithmetic, adding, subtracting, multiplying, and dividing using our base set 10 system, our decimal system. So we owe that to Fibonacci. And it was all in this book he wrote called Liber Abaci. And there was only 2 pages of this book devoted to Fibonacci numbers. So Fibonacci numbers was just a small, almost like a footnote in Liber Abaci. But he presented Fibonacci numbers as a sort of a mathematical exercise involving rabbit breeding. He came up with a kind of a thought experiment. I think we would call this a thought experiment today. Kind of light of what Einstein and a lot of other physicists have done. Just you think about kind of a hypothetical situation and see what results from it. So here's the situation. We start each year. So you start the year with a single pair of newborn rabbits. And I think you guys all know that rabbits breed very quickly. So these rabbits do too. So after 1 month, the pair of rabbits becomes fertile. And then after another month, and each month thereafter, a fertile pair of rabbits gives birth to another pair of rabbits. So it really takes them like 2 months to give birth. It takes them 1 month to become fertile after they're born, and then another month to give birth. And they give birth to a single pair of rabbits every month. Once they're fertile, they keep doing it for the rest forever, and they never die either. That's another simplifying assumption. So because they never die, you can see that their population is going to grow very fast. Essentially, grows exponentially. And you might wonder, how many rabbits do you have after each month? Well, it turns out the number of rabbits after each month is a Fibonacci number. I mean, after zero, you just started at 0 months with one pair of newborn rabbits, but then after 1 month, you've got one pair of fertile rabbits. But then after 2 months, the fertile pair gives birth to a pair of newborn rabbits, and now you have two pairs of rabbits. And then after 3 months, you have to kind of keep pair of the newborn pairs and the fertile pairs. And remember, the fertile pairs never die, and they keep giving birth to a new pair every month. So after 2 months, you have one fertile pair, one newborn pair. After 3 months, the fertile pair gives rise to another pair. So now you got two. You've got another newborn pair, and you've got the original fertile pair that gave birth. But now the newborn pair from the previous month becomes a fertile pair. So now you got two fertile pairs and one newborn pair, and you keep going like that. There's three pairs altogether after 4 months, I guess. And I mean, I'll just summarize what you get. So if you look at, I mean, actually, I don't do that yet, but um, here's the table that shows you the first 13 Fibonacci numbers. I'll just cut to the chase here. So this is the number of pairs of rabbits after each month, and you see that at the beginning of the 13th month, I think usually people only go up to the 12th month actually. So by the 12th month, there's 144 pairs of rabbits. You might not expect that many, but there are. Actually, after the 13th, at the beginning of the next year, you'll have 233 pairs. But you might wonder, how do you get these numbers in this sequence? Is there an easier way than just keeping track of the fertile pairs and the newborn pairs? Well, as it turns out, there is, and that's what this big description is all about here. You can give different names to the sequence of fertile pairs. I think I call those GN, and the number of newborn pairs HN. And you can see that Fn is always equal to Gn plus Hn, because every pair of rabbits is either a fertile pair of a newborn pair. And then you'll also know that after another month, each newborn pair becomes a fertile pair. That means that Fn plus 1 is equal to Gn. That was the number of newborn pairs for the previous month, plus the number that you had, the number of fertile pairs you had in the previous month, Fn plus Gn. And similarly, Gn is equal to Fn minus 1, because whatever fertile pairs you had the previous month are going to give birth to a newborn pair. And if you solve both of those equations simultaneously, I'm not going to go through all the details, I do it in the book here, but you come up with a single recurrence equation for the Fibonacci sequence, Fn. It turns out that Fn is equal to Fn minus 1 plus Fn minus 2. In other words, the number of pairs of rabbits you have to after n months is equal to the number you had after n minus 1 months in the previous month, plus the number you had 2 months ago, Fn minus 2. You can check that yourself. This is what's known as the recurrence formula for the Fibonacci sequence. And it turns out that the only other information you need to completely define the Fibonacci sequence, you have to have a set of initial conditions. You need to have exactly two. So you have to know what F1 and F2 are. And if we define both F1, in other words, the number of pairs of rabbits after 1 month and the number after 2 months, and we define those to each be equal to 1, then this completely defines the Fibonacci sequence. I mean, I think you can just apply the recurrence equation to get F3 from F1 and F2. F3 is F2 plus F1, which is 1 plus 1 or 2. F4 is F3 plus 2, which is 2 plus 1 or 3. This is the easier way to do it. Just add the two numbers, previous numbers. F5 is F4 plus F3, or 3 plus 2 or 5. Keep going like that, and you'll get the sequence. And you can go till the cows come. I mean, and these things do get really, really big. And, this is as far as Fibonacci went, describing a sequence. But it turns out, I mean, Fibonacci numbers are much, much more robust than you might think. As a matter of fact, there's a whole journal called the Fibonacci Quarterly. And I've actually published 3 math papers on the Fibonacci Quarterly. You can look for my name on the Fibonacci Quarterly. I published two, I think, in 1994 and one in 1996, if I'm not mistaken. I don't remember, but anyway, it's a very prolific journal, and you might want to check it out. And you also might want to check me out on there, to my own horn a little bit. I talked about stuff a lot more advanced than this, needless to say. But anyway, that concludes my talk for today on Fibonacci numbers. So thank you for watching. Long live math, and I'll see you guys next time. Bye.